Welcome. Today I'll talk about fluid mechanics in computer and computer-related cooling systems. Some components of particular importance in this regard may include the heatsink, the fan, the pump, the radiator, and of course the coolant itself. Now I'll discuss the fluid mechanic principles of convection and conduction present in each component before concluding with a brief comparison between coolant-based cooling systems and airflow-based cooling systems measured by the aforementioned principles. First off, heat sinks. The point of the heatsink is to maintain a particular temperature in order to prevent possible overheating or even prolonged so-called cool-off periods. Basically, the heat generated by the electrical equipment is transferred to the base plate from where it spreads throughout the whole available surface area before dissipating into the atmosphere from the fins in the radiation phase. Many different types of heat sinks exist. Passive heat sinks, which make use of natural convection, active heat sinks, which make use of some sort of fanning device to generate stronger convection, and liquid-cooled heat sinks, which make use of some sort of liquid coolant, not unlike a fridge. Now onto fans. Fans accelerate airflow, which consequently accelerates the dissipation from the heat sink by optimizing the convection stage. This, of course, increases system reliability and performance. Adding fans to a CCS can easily increase heat dissipation by about 50%, which corresponds to a 10 to 20 degrees Celsius reduction in component temperature. The optimization challenges, however, have more to do with power consumption and noise generation trade-offs. Lastly, pumps and radiators. Where fans and heat sinks, for the most part, make use of air-based cooling, pumps and radiators primarily make use of coolant-based cooling. Pumps and radiators still utilize convection and conduction to achieve the same goal. In fact, radiators have built-in pumps. Pumps act as the transport medium for the coolant, and radiators as the coolant equivalent of the heat sinks in the airflow cooling system. Pumps create a pressure difference by converting mechanical energy to fluid energy by making use of familiar strategies such as centrifugal forces, positive displacement, and other rotordynamic mechanisms. The low pressure zone on the suction side draws the fluid into the pump, and conversely, high pressure zone on the expulsion side expels it. Hence, the pressure gradient assists the movement of the coolant throughout the system. Consequently, pumps cause a forced convection effect, making pumps in this sense analogous to fans in the purely airflow-based cooling systems. The viscosity of coolants in these coolant-based temperature-controlled systems are relatively low, especially when compared to coolants in refrigerators, for example. The reason for this is both practical and economic. Some reasons are temperature and flow-related aspects. Coolants here operate within a narrow temperature range and, of course, need to be optimized for turbulent flow. Now, the benefits of having more turbulent flow present include enhanced heat transfer and increased convection. Low viscosity coolants assist in the creation of these circumstances by decreasing the denominator in the Reynolds number definition. And of course, less viscous coolants require less energy to initiate movement. Radiators provide more surface area for heat transfer, enhancing convection. Additionally, built-in fans generate airflow, also resulting in increased heat transfer. Radiators, similar to heat sinks, make use of materials with high thermal conductivity, such as copper or aluminum, to extirpate heat more efficiently. All the components of radiators are designed to minimize thermal resistance, resulting in the minimization of the temperature gradient according to the given equation. This results in better component performance and consistency, reduced component strain, and overall improved system stability, reducing the risk of localized overheating. Now I'll briefly elaborate on the apparent differences between LCSs and ACSs. Water, a commonly used coolant in CCSs, has a relatively high heat capacity, about 4 times higher than air at the relevant temperature and pressure for CCS purposes, which makes it a better medium for heat transfer than air. Coolants also have higher heat transfer coefficients and greater, more consistent, and more controllable flow rates. Therefore, liquid-based cooling systems enact great convection. Coolant-based cooling systems have lower temperature gradients and higher cooling capacities than airflow-based cooling systems, but typically cost more, take up more space, leave less space for other components one might want to add, and obviously leads to a higher susceptibility to corrosion of electrical equipment. Due to the liquid's more direct contact with components, thermal interface resistance is greatly reduced, and due to the higher thermal conductivity of coolants, conduction is generally vastly better in liquid-based cooling systems. Overall, liquid-based cooling systems are considered better performance-wise, but the disadvantages are significant enough to validate rather choosing an airflow-based cooling system. Thank you for your time and enjoy the rest of your day.